This unique feature allows production of a complex or customized part directly from the design of CAD model without the use of expensive tool. Next, classification based on energy sources for direct energy deposition. In this process, focused thermal energy is used to fuse the material by melting as they are being deposited. Direct energy deposition can be used to fabricate parts made of metal, alloy, metals, alloy, polymers, ceramics, and composites. Direct energy deposition following advantage like ability to manufacture complex geometry parts, ability to economically repair damaged components or products, or ability to modify surface of a product by coating. Next, figure show the classification of direct energy deposition process for the metallic material according to the type of energy sources used. Energy beam and arc based are commonly used heat sources in different additive manufacturing process. In energy beam based process, use either laser or electron beam as a heat source. They have high heat transfer efficiency and yield very good quality of deposition, but they are very costly and low deposition rates, and more suitable for minimum size of additive manufacturing of metallic material. But arc based deposition process are categorized into two category: process which directly use arc for material deposition, and process which use arc for formation of plasma and which provide heats for material deposition. These processes have lower capital and operational cost and gives higher deposition rate. Next, additive manufacturing of metallic material by microplasma transfer arc process. In this process, a pilot arc is generated inside the deposition head, which generates plasma between the deposition head and substrate. Plasma is forced to pass through the concentrated nozzle, and the deposition head thus accelerate and towards the substrate, and powder fed through the coaxial nozzle gets melted and deposited sorry, to form a bed. Figure represents the concept of deposition of layer and track used in additive manufacturing process. Single layer, single track deposition, which is typically used for repairing or remanufacturing application. Next, single layer multi-track deposition, which is typically used for various coating application. Next is multi-layer single track deposition, which is generally used for manufacturing thin wall complex structure geometry. And the final is the multi-track multi-layer deposition, which is used for cladding application and manufacturing thick walled complex geometry. Next, application of additive manufacturing of metallic material. Various application of additive manufacturing have evolved and which can be categorized into four categories. First is the solid free from fabrication, that is rapid manufacturing. Major application in direct manufacturing of component required in aerospace, automotive, household, and biometric applications, some of which are shown in the figure. Next, in the rapid tooling, manufacturing of different tools such as uh, uh, forming die, mold of plastic parts, metal pattern, some of as shown in the figure. Next is the repairing and remanufacturing. Expensive and difficult to manufacture components such as die and mold are subjected to some repairable damage during their use. And next is the surface modification. Figure show the surface modification of a cylindrical component and single point cutting tool by additive manufacturing process. Next, review of the past work on arc-based additive manufacturing process. In the first literature review, the author used microplasma tungsten in a gas process for additive manufacturing of Inconel alloy 6 series. And the final conclusion is that manufactured parts are fully dense and with no cracks and pores, and the maximum tensile is set approximately 690 megapixel and the hardness is 158. In the next literature review, it is use of plasma transfer wire arc deposition process of titanium alloy wire, and achieve that the deposition efficiency is 93% and the deposition rate of 1.8 kg per hour. In the next literature review, the author uses microplasma transfer wire deposition process for ASI P20 steel, and so that process is capable for manufacturing straight wall of width 2.45 mm. And they also found that 87% of deposition efficiency and the maximum deposition rate is 42 gram per hour. The next literature review, in the next The author use plasma transfer arc additive manufacturing of titanium alloy wire is used for deposition, and generally so that a multi-layer deposition had approximately 900 megapascal yield strength and approximately 99 megapascal of ultimate tensile strength. In the next detailed review, the author used microplasma transfer via deposition of stellite 6 powder particle of size 55106 micron. And the final conclusion is that deposition height decreases with increase the microplasma power and travel speed. And the multi-track deposition has coarser dendritic microstructure than that of single track deposition, and micro hardness of multi-track deposition of stellite is higher than the substrate and decreases with microplasma power. Next, the identify result get no work has been reported on the development of functionally graded material having properties similar to that of human bones by microplasma transfer arc deposition process. No work has been reported on the use of cobalt, chromium, titanium powder for orthopedic implant and its vitro biocompatible evolution form and mechanical characterization. No work has been reported on the use of high entropy alloy for orthopedic implants and in vitro biocompatibility evolution and mechanical characterization. Limited work has been reported on the manufacturing of knee implant by powder metallurgy, direct energy deposition based additive manufacturing process such as selective laser melting and electron beam melting. No work has been reported on manufacturing of knee implant by microplasma transfer arc deposition process. And the final research objective of the present work, development of the functionally graded materials such as cobalt, chromium, titanium powder, and high entropy alloy by microplasma transfer arc deposition process for orthopedic application, and identify their optimum condition through in vitro biocompatibility evolution and mechanical characterization. Study the effect of microplasma transfer arc process parameter on lattice structure, porosity, biocompatibility, and mechanical property of the developed functionally graded material. Identify optimum parameter of microplasma transfer arc process for additive manufacturing of the optimized functionally graded material. Additive manufacturing of knee implant by microplasma transfer arc process and maximize surface finish and surface integrity of the manufactured knee implant. Performance analysis of the best quality manufactured knee implant through evolution of in vitro biocompatibility, mechanical property, wear analysis, and corrosion behavior. Next, experimental apparatus for microplasma transfer powder deposition. Figure A and B generally show the systematic diagram and experimental apparatus of the microplasma transfer arc powder deposition process. It consists of various parts. First is the power supply unit, that is DC power supply is used, and next the deposition head and microplasma torch. Deposition head was developed to deliver the deposition material from the powder feeding system to the melt pool, and microplasma torch generally consists of tungsten electrode, concentric nozzle, gas line external, and plasma formic gas is supplied through the concentric nozzle, and cooling water is also used to prevent the overheating of the microplasma torch. Power feeding system generally consists of the hopper, mixing unit, and flow control valve and the nozzle. And next is the manipulator system. In order to continuous and precise of the deposition and along XYZ axis, a manipulator system was subsequently developed. Next, the process parameter of use for microplasma transfer arc powder deposition process. Figure represent the important process parameter of microplasma transfer arc process. For one in the microplasma power supply, second one the deposition process parameter. In microplasma power is plasma power, plasma gas flow rate, and shielding gas flow rate. In deposition process parameter, powder mass flow rate, travel speed, and the last is the standoff difference. These are the references that we will use in my presentation. And thank you. Thank you, sir.
Pradman, it was a good presentation, and most of the things you have incorporated. Who is next? Okay. Continue, please. Who is next?
Sir, am I audible to you?
Yes.
Yes, sir. I am just sharing my screen so that we can.
Janmejay, your voice is coming very low.
Sir,
is it okay now?
Is it audible now?
Yeah. Please continue.
Yes, sir. Sir, I am just sharing the screen